So today Professor Qiu will present control chart for dynamic processing monitoring. And let me first introduce, it's my great pleasure to have Professor Qiu in this webinar. Dr. Qiu is the Dean, professor and the founding chair of the Department of Biostatistics at U of Florida. He got his PhD in statistics from the University of Wisconsin-Madison in 1996. Dr. Qiu also has made many significant contributions to the jump regression analysis, image processing, statistical process control, survival analysis, dynamic disease screening, and spatial temporal disease surveillance. He has authored 3 books and published over 170 research papers in leading refereed journals. He is also an elected fellow of American Association for the Advancement of Science, American Statistics Associations, American Society for Quality, and the Institute for Mathematics Science Statistics, as well as an elected member of the International Statistics Institute. Dr. Qiu also served as editor for Technometrics, and he is also the recipient for the prestigious Sword Medal. So let's welcome to Dr. Qiu one more time. And so if you have questions, please mute yourself first, and you can type your questions in the chat box, and we try to answer those questions in the final Q&A session. Professor Qiu, the floor is yours.
Okay, thank you so much, Bo. And also I want to thank Qiu and Bo for inviting me to give this seminar presentation. And I told them that QSR is always my favorite organization. And I went to Inform's QSR meeting almost every year and other activities as well. And today I just want to introduce some of our recent research on dynamic process monitoring. And this research, by the way, is a collaborative research with my either existing students or former students, including, including my students, former student, Xuling. I just saw his name in the audience. And first, let me introduce the problem by using an example about air quality monitoring. And we know that air quality monitoring is very important for public health improvements and so forth. And there are a lot of air pollutants. For example, the major ones are the carbon monoxide, CO, and PM 2.5 and others. And so in the United States, actually, we have many called air quality monitoring stations, like this one. This is one station. And there are hundreds of, more than 200 stations in the United States, actually. And those air quality monitoring stations collect data in hourly basis, okay? Hourly basis means every hour, for example, they will collect data about the CO level, intensity level, and PM 2.5 intensity level at those places, specific places. So then what the data they collected looks like. So at each hour, each time, we have a vector, long vector, right? Each component, each element is the air pollutant. Then we have observation of that long vector over time, every hour. So it's a multivariate data stream. Data stream means data keep coming, just like a river. The water is flowing all the time. So, so the data collected by those air quality monitoring stations are in the format of multiple data streams. And now this is one specific data set we used in several of our papers. This data actually collected by the Beijing government. Beijing government developed a pollution alert system in late 2013 because at that time, air pollution is very serious in China. For those of us visited China quite often, we know that about 10 years ago, air pollution is very serious in China. So the Chinese government realized that. So they, Beijing government started to develop this system in late 2013, collect air pollution data. And then, so that this plot displayed observed daily density levels of PM 2.5, that's the first panel, and the CO, that's the second panel, and the dew point temperature, that's the third panel. And the first two are the air pollutants, but third one is a kind of weather variable, but that variable, meteorologists find that variable is closely related to the air pollution. So the data, so here we consider three-dimensional vector. And then we have data every day. And here, this figure displays the data in 2 years, okay, separated by this vertical dashed line. And we started from March 1st because remember this air pollution alert system developed in late 2013. The first couple of months, actually data not that complete. So data becomes quite complete starting from March 1st. That's why we display data, analyze data from March 1st. And from this data, you can see that, first of all, there are some seasonalities, yearly seasonality, you can see. For example, the CO, for example, level, this is the winter time, is quite high in the winter time and relatively low in the summertime. Okay, and the dew point temperature also has yearly seasonalities, and that's typical. And because in the wintertime, the northern part of China, they use a lot of coal, 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 as the major energy resource. So make the pollution quite serious. And also in this data, meteorologists, after they've analyzed data, they find that the first year, the air pollution is not very serious. It's quite a typical year in Beijing. But the second year, you can see those levels quite high. Now, we want to develop some control chart to monitor this kind of multivariate data streams. So let's now talk about statistical process control. So it's about sequential process monitoring. And sequential process monitoring is mainly for monitoring data streams, as I mentioned. New data keep coming over time. And then one fundamental research question about sequential process monitoring is that we want to know whether the underlying longitudinal process behave as expected over time or not. Okay, so at each time point, we need to make a decision whether its behavior, the underlying process, behavior of the underlying process is as expected or not. And so the major statistical tool is statistical process control, provide a major statistical tool for sequential process monitoring. And so far, I gave an example about environment, but actually production lines in manufacturing industries, for example, use statistical process control a lot, and also internet traffic monitoring and surveillance of infectious disease and so forth. There are wide applications about how to monitor these data streams. Now, for this audience, I believe all of us know some basics about statistical process control. So I will go through those slides very quickly. Basic statistical process control charts. First, we have Peihua chart. Although this is the popular book we often cited, but actually the first Peihua chart, Peihua developed first chart about exactly 100 years ago. That's in 1824. Exact 1 year. But this is a book, so we often cite this book as the kind of first literature on Peihua chart. And the Peihua chart make any decisions based on the observed data at the current time point only. Didn't make use of the historical data. So then how to make use of historical data? Then we have cumulative sum charts, we have EWMA chart, and we have change point detection charts. And those are four basic type of control charts. Each type we have hundreds of, even thousands of Peihua chart. I don't know how many, I didn't count. Must be hundreds of Peihua charts. So each category has hundreds of different versions. And when the data stream or process behave as expected, then we say that the process is in control. Otherwise, the process is out of control. So we want to distinguish out of control from in control, basically. And then the performance measurement is we use in control average run length, AIL0, and out of control average run length, AIL1. And we usually set AIL0 at a given level, then minimize, try to make the AIL1 as small as possible. So I don't want to explain those concepts in detail for this audience, but in the case you have questions, you can ask me. I can explain those in more details. And then the conventional control charts, those classical control charts, are designed based on the classical conventional assumptions that the in-control process observations are independent and identically distributed with a parametric, such as a normal distribution, when the process is in control process. Okay, right? And but in reality, all those assumptions are really valid. So that's the issue. And if you want to know more about those basics about control charts, you can read my book published about 10 years ago. So the conventional SPC charts could be unreliable when one or more of their model assumptions are violated. And in the environmental data I presented before, IID normality, all those assumptions are violated. Here, let me present another data set. It's about the incident rates of a disease. This is actually flu incident rates in Florida on 2 specific days. This is the summertime, June 1st, 2012. This is the winter time, December 1st, the same year, 2012. And the color denotes the value. The color stronger means the value is larger. In the summertime, incident rate will be lower. Wintertime, incident rate will be higher. Even in this specific year, 2012, epidemiology already confirmed that there are no major disease outbreaks. It's a regular year. But you can see that the in-control distribution at the different time points are different. In the summertime and the winter times are different. In-control distribution will change over time, right? And also the data we double check, data are spatially correlated, also temporally correlated. And we checked that the normality assumption, Poisson distribution, all those distributions are not valid here. Okay. IID normality, all those assumptions, none of those assumptions are valid in this specific data set. And in this audience, I just want to mention, because I read your papers so often that I feel that we usually don't check the model assumptions very carefully when we publish papers or write a grant proposal. And now what's the consequence? If one or more assumptions are violated, but you still use the conventional control chart, what's the consequence? I use this toy example. Assume the in-control distribution is normal 0, 1. That's the in-control distribution, normal 0, 1. But the actual distribution is the standardized version of chi-square distribution. Standardized version means we make the mean to be 0, standard deviation to be 1. But its shape is skewed. It's chi-square distribution. Degrees of freedom, let the degrees of freedom change, for example, from 2 to 60. Then the nominal or the assumed AIL0 value is 500. So we assume that distribution is normal, but actually it's a chi-square distribution. And we try to use the conventional Q-sum chart. And the assumed AIL0 value is 500, but this line denotes the actual AIL0 values. When the degrees of freedom is very small, for example, the distribution is very skewed. The actual distribution is chi-square distribution. Very skewed, the actual AIL0 values will be far away from the nominal value of 500. What's the consequence of this? Consequence of this means this kind of control chart actually not reliable. All the results are not reliable. We will get the signal much more frequently than expected. Okay, just like in hypertesting, the assumed type 1 error probability is 0.05, but the actual type 1 error probability, for example, is 0.7. This kind of hypertesting procedure cannot be used. That's why I remember from time to time when I attended the Informs conference, there are many friends often ask me, Dr. Qiu, why you check those assumptions, want to check those assumptions? And why those assumptions? It's important to check those assumptions. That's the concept. That's why it's important. And this plot showed a similar fact, but the actual distribution, T distribution, instead of chi-square distribution, it's T distribution. X-axis is also the degrees of freedom. Actually, that's the motivation why 25 years ago, I want to spend a lot of time in SPC. Originally, I don't do any research in SPC. In 1998, after I joined faculty in Minnesota, and but after reading a book by Doug Hawkins, and I found that all the methodology described in that book assumed IID normality or something like that. So then I checked. When one of those assumptions are violated, then the results are not reliable. So I already spent over 25 years to try to develop more flexible control charts. And then in the literature, we have one research area called non-parametric SPC, try to get rid of the normality. And then there are a lot of methodology already developed. Mainly, the main idea is instead of monitor the original data, we use the data ranking or data categorization. Category data, then use the categorical data analysis to do process monitoring. And this is a kind of overview paper I published a couple of years ago. If you are interested in non-parametric SPCs, then you can read this paper or my book. And then there's another, so this area try to get rid of the normality, parametric distribution assumption. And then about 12 or 13 years ago, I I initiated a research area called the dynamic screening systems. That research area is mainly for monitor processes when its in-control distribution change over time. And I actually, that kind of research is motivated by disease screening, try to detect, for example, stroke, a disease, a specific disease like a stroke, as early as possible. Then each patient can be regarded as a process. And we monitor the disease risk factors of each patient. So each patient is a process, monitor disease risk factors of a patient. And even for healthy people, for healthy patients, its disease risk factors will change, in-control distribution will change over time. Okay, so we monitor a population of dynamic processes by using dynamic screening system because each patient is a process. So we have a population of patients. Okay, that research area try to get rid of the identical distribution assumption. And the first paper is published in Technometrics, Qiu and Xiang. This is a Technometric paper. And then there's another research area, try to monitor processes with correlated data. Data are correlated. And in this research area, my friends, for example, Fuji and Dan Apley, Fuji Zhong, and Giovanna Capizzi, all those people already do a lot of work, research on that topic. If the data are correlated, then how to handle that? Their major idea is to use time series modeling. And then got a residual. Instead of monitor original data, we can monitor the residuals. That's their major idea. But I always ask them, I said, how about in situations when the time series model themselves, those models, parametric models, not valid? Usually they never checked whether those time series models are valid. And so I myself write a sequence of papers already. We try to get rid of the time series models. We try to use a moment estimation of serial correlation. And moment estimation is non-parametric. We didn't put any parametric models to describe the autocorrelation. You may ask me, if the data are correlated, you ignore the data correlation, what will happen? Similar situation, I have plots actually, similar plots, just like the plots, just like this, those plots. The actual AIL0 values will be far away from the nominal AIL, assume the AIL0 value. So the control charts actually cannot be used. And then in recent couple of years, we have many machine learning approaches. Machine learning approach try to approximate a real world problem by computer algorithm like random forest after learning the data structure from a training data, right? And then we have supervised learning and unsupervised learning. Supervised learning require training data contain both in-control and out-of-control observations. In manufacturing industries, usually at the beginning of process monitoring, we usually don't have out-of-control observations. So in SPC, typical SPC applications, out-of-control observations are often unavailable in advance, right? So then to get rid of that difficulty, George Runger and his student developed a methodology called artificial contrasts. They try to generate some artificial out-of-control data set from off-target distribution like a uniform distribution. But of course, those artificial out-of-control data set may not describe the actual out-of-control data well. So then they later on, they suggested another idea called a real-time contrast, also by George Runger and his former students. And then at the current time point, they consider windows. And then observation in that window of the current time point, they consider that observation as out-of-control data. Then they combine the out-of-control data into the in-control data collected at the very beginning. Then they apply a random forest or something like that, got the decision rule, then use the decision rule for process monitoring. And then Fuji and his student, they suggested a one-class classification because, as I mentioned, we only have in-control data at the very beginning. So that's one class. We don't have out-of-control. Then for the initial in-control data, they try to find a boundary of the in-control data. And they use the boundary as a decision rule. For future observations, if future observation located outside of that boundary, then they claim the process is out of control. Otherwise, it's in control. Okay, but those all those machine learning approach work as a black box because their performance depend on, for example, how well the training data represent the test data, how large the training data is, and so on, and how the decision rules are constructed, so on and so forth. And we don't know when they will perform well, when they will not perform well. So they are black box. And so in the case you are interested in machine learning approaches, a couple of months ago, I wrote a small article for this online journal. And now let's come back to today's topic about online monitoring of dynamic process. So here, dynamic data stream means new data keep coming and in-control distribution can change over time. Okay, keep in mind that the pollution data, even in a specific year, the pollution is typical. There is no outbreak. Wintertime, summertimes are different. The in-control distribution will change over time. And in this area, we already, here we focus on monitoring single dynamic process instead of a population of dynamic process. If it's a population of dynamic process, like patients, then we have a research area called the dynamic disease screening. Remember, dynamic screening systems. We have another. So here we focus on monitoring single dynamic process. And we already published a number of papers here. I will briefly mention 3 of those papers. The first paper, published in Technometrics 2 years ago, suggested a concept called transparent sequential learning for monitoring processes with correlate data. And then the second paper, published in Annals of Applied Statistics, is for monitoring dynamic process with the application to air pollution surveillance. Third paper, also in Annals of Applied Statistics, is a generalization of the second paper to the cases, generalize the second paper approach to cases when there are a lot of high-dimensional data. There are many variables to monitor. Then we need to use a PCA-based sequential learning. So let me briefly introduce the transparent sequential learning concept. I keep telling people, I say that although we SPC people never really mentioned machine learning 10 years ago, but we actually used the machine learning idea all the time in the entire area 100 years ago. For example, in SPC, usually we collect a small integer data set, routinely collected after phase 1 analysis before the online monitoring, right? And then why to collect this small integer data set after phase 1? Then from this data set, we try to estimate some integer parameter like integer mean, integer standard deviation from the initial integer data, right? That's a learning. Although we never use the concept called, use the terminology called learning. We learn those unknown parameters from the integer data, okay? And remember, my colleague, Dr. Hawkins, initiated a research area called self-starting control charts, remember? Self-starting control charts means, in many cases, our initial integer data is very small. So the estimates of the integer mean, integer standard deviations, their variability could be quite large. So his idea is, at the current time point, if our decision is that the process and the monitoring is in control, let's combine the observed data at the current time point with the integer data. Then let's update the estimates of the integer parameters by using the combined integer data, updated integer data. That's the idea of self-starting control chart. That's a sequential learning. Sequential learning means the training data keep being expanded. And what we learn keep being updated. That's sequential learning. What's more is that what we learn from the integer data are well defined in advance. For example, we want to learn integer mean, integer standard deviation. So that's transparent sequential learning. The learned, for example, we often use sample mean to estimate population mean. Their statistical properties can be well derived. We know when they will perform well, when they will not perform well. So that's the concept of transparent sequential learning. So the transparent sequential learning, then in this specific paper, Technometrics, we generalized the self-starting control chart in make it more general. Under this transparent sequential learning framework, that's my own terminology. Actually, I spent several years to come up with this terminology. So assume the in-control process distribution is F0 does not change. So in this specific paper, we are not handling dynamic process. We are handling regular process. In-control distribution does not change over time. And those are the quality variables, p-dimensional quality variables. And then we have initial in-control data. Initial in-control data, this M0 is the sample size. And then the process characteristics to learn from the in-control data, one is the in-control distribution. Another one is the correlation among observations at the different time points. Those things are the things we want to learn from the in-control data, okay? And then in this first paper, we assume that the correlation is stationary. Stationary means the covariance, this covariance only depend on S, does not depend on I. If two observations are S units away in observation times, then their correlation is gamma 0 S, only depend on S, okay? That's a stationary correlation. And also in this paper, we assume that the correlation is short range. Short range means when the two observations, their observation time farther away, the correlation is smaller and smaller. And then if the observation time difference is larger than Bmax, then the correlation can be ignored. So Bmax describes the range of correlation, temporal range of correlation. So short range is the stationary correlation. So, so in this specific paper, for the distribution, we said that for the distribution, in-control distribution, we mainly interested in estimating mean and covariance matrix. And then for the covariance, we are interested in learning gamma 0S, so it's gamma 0S, okay, in this range. That's what we learn. So what we learn from the in-control data are well defined. And then from the initial in-control data, we estimate those parameters, in-control parameters, by using kind of moment estimation, because we don't want to put any parametric assumptions, distribution assumption. We don't assume the distribution. Otherwise, we can use MLE. But here we use moment estimation, okay, for mu 0 and the gammas and so on, and the sigma. And then for monitoring, now this is for online monitoring. This is the observed data at N's observation time in phase 2. after this data is collected, after the data is collected at the current time point, first we do the recursive data declaration. Because the conventional, remember, conventional control charts are only valid when the observed data at different time points are uncorrelated. So we do the data declaration. We decorrelate xn with all previous observations. How to decorrelate? Remember, the covariance matrices, all those has been estimated in advance from the integer data. Remember, the gamma zeros, all those are estimated. So by using Cholesky decomposition of the covariance estimated covariance matrices, we can do the decorrelations over time. Okay, then we apply a non-parametric control chart to the decorrelate data. Then if there is a signal, then we try to figure out what's the root cause. If there is no signal at the current time point, then we combine xn with the in-control data. And then we update the in-control parameter estimates by using the expanded in-control data, by using the combined in-control data. Okay, so the in-control data keep being expanded, and then the in-control parameter estimate keep being updated. This update is a recursive update to save some computing time. And so this is the diagram. So there is the initial in-control data. We do the initial estimation of the in-control data. Then at the current time point n, after the data are collected, we do the decorrelation, then apply a control chart. Whether detect a shift or not. If yes, then we give a signal. And otherwise, combine xn with the in-control data, and then update estimates of the in-control parameters. Then the online monitoring proceeds to the next time point. That's the concept of so-called transparent sequential learning. Transparent means what we learn are well-defined. Their statistical properties can be well-derived. Transparent. Sequential learning means the in-control data keep being expanded, and the in-control parameter estimate keep being updated. Transparent sequential learning. And then in this paper, now this paper is talk about dynamic processes. Okay, dynamic processes. And so basically this paper is a kind of generalization of our first paper, transparent sequential learning. First paper I mentioned, the Technometrics paper, generalize that methodology for monitoring dynamic processes. So again, we choose the initial in-control data, or we choose the baseline data. Okay, for the pollution data, we choose, for example, we use the previous year data, for example, previous year data as the baseline data, or initial in-control data. And if seasonality is relevant, then this initial in-control data need to cover at least one whole period. Okay, otherwise the periodic pattern cannot be estimated well. Then we estimated the so-called regular longitudinal pattern of the process from the initial in-control data by using non-parametric curve estimations. Okay. Then for the monitoring, after the data are collected, then we first standardize the collect data, observe data. Standardize, how to standardize data? We minus the mean divided by standard deviation. Mean and standard deviation are from the estimated regular longitudinal pattern. And then we do the data decorrelation again, decorrelate the standardized data at the current time point with all previous data. And then we apply a control chart to the standardized and decorrelate data. And then give a signal if shift is detected. Otherwise, combine the current observation with the in-control data and update the estimated regular longitudinal pattern using the combined in-control data, and then proceed to the next observation time. So the only difference is that we need to do the standardization, estimated regular longitudinal pattern from the initial in-control data, and then after the data collected for monitoring, we need to do the data standardization by comparing the observed pattern with the estimated regular longitudinal pattern. Okay. And the technical details are here. I don't know. Yeah, maybe I should skip the technical details. This is the initial in-control data. And then from the initial in-control data, we first use a non-parametric approach, motivate non-parametric longitudinal models. Estimated mean, estimated covariance matrix, covariance functions. Mean and covariance functions, only assumption we made are that they are continuous functions. We don't put any parametric forms on those functions. And then we have a specific approach to estimate those mu and v. And then those items are for monitoring. I don't want to save some time, I don't want to go to the details about those. If there are no signals, then combine the current observation with the integer data at the previous time point, got the updated or expanded integer data. Then all the function estimate need to be updated as well, updated from the previous time point, and then proceed to the next time point. And this is the, remember this data I presented before about air pollution data in Beijing. The first year data is in control. Meteorologists already confirmed. First year, there are no major air pollution outbreak in this year. So we use this data as the in-control data, try to monitor the second year data. And then the first line, first row, this is the first year data. Remember, we have three variables. This is PM 2.5, this is CO, this is DEW. And then those are the observed data. The dark solid line denote the estimated mean, by using non-parametric curve estimation. Okay, estimate mean. And this is the second year data. This is second year data. Second year data, remember, when we monitor the second year data, we need to keep updating our estimated mean function. So this solid line denotes updated mean function, updated during online monitoring. Okay, and then we gave a signal at this time point. This denoted the signal time point. So we gave a signal around maybe November 19th or something like that. I forgot the specific time. And then the third line, we put the first year data and the second year data in the same plot around the signal time. Okay, so the dotted curve denote the first year data, dotted curve denote second year data, solid curve denote the first year data around the signal time. You can see that the 2 year data are very similar at the beginning, then start to deviate, for example, at the beginning of November. Then our signal is here. So our signal looks quite reasonable here. And that's the dynamic monitoring. But by using this approach, dimension is only 3. But in many applications, the dimension could be, in this paper, for example, the real example we used in this paper is, I remember, is 70-something dimensionality. There are 72 or 76 variables we want to monitor. And in many, for example, semiconductor, we can easily, semiconductor manufacturing, we can easily monitor several hundreds of variables, additive manufacturing or something like that. And so if the dimensionality is very high, then how to monitor so-called high dimensional dynamic process. So that's the topic of this third paper, published a couple of months ago, several months ago. Again, we need to choose the initial integer data. That initial integer data may not be that very large. Then we try to from the initial integer data, we try to estimate the regular longitudinal pattern. And based on the regular longitudinal pattern, we can standardize the initial integer data, minus the mean divided by standard deviation or something. Standardized initial integer. Then we can compute the PCA, first principal component, second principal component, those Lord matrices, Lord coefficients, and so on and so forth. And then we need to decide how many PCAs we should use, right? And then for online monitoring, at the current time point in, during online monitoring, we first standardize the observed data at the current time point by using the estimated regular longitudinal pattern. How to do that? Minus the mean divided by standard deviation. Right? Mean and standard deviations are estimated from the got from the estimated regular longitudinal pattern. But of course, in high dimensional cases, the data standardization is a little bit more complex in matrix format, not just minus the mean divided by standard deviation. There is a matrix operations. After standard data, we apply PCA to the standard data for dimension reduction. XN now already standardized. Then we apply PCA. For example, then we calculate, for example, suppose we only use the first two PCAs, then the problem becomes two-dimensional. Apply PCAs. And then the PCA at the current time point, PC data, at the current time point need to be decorrelated with previous PC data. And then we apply a control chart to the decorrelated PC data. And then if no signal is triggered, then we combine the current observation with the in-control data, update all parameters, in-control parameter estimates, PCA parameters, everything, and then proceed to the next time. If there's a signal, just give a signal and make the post-signal diagnosis. And I didn't go to the detail. Actually, it's much more complicated than this. For example, at each time point, how many PCAs we should use? We said, suppose we should use a number of PCAs such that 90% information need to be preserved. Then if 90% information should be preserved, then the number of PCAs at different time points could be different. How to handle this kind of details? All those details actually are discussed in the paper. We have some theorems. So we prove that the number of PCA actually will be stabilized over time. And also, I already spent more than a decade, more than 10 years for monitoring spatial temporal dynamic process, okay, for disease surveillance. Disease surveillance, remember the data I presented to you, flu data, each day we got spatial data at the different counties or something like that, of a state, of Florida. And then we collect spatial data over time, so spatial temporal data. For this kind of spatial process, its in-control distribution will change over time. The incident rates in the wintertime and the summertime are different. So that's also dynamic spatial processes, how to do a spatial temporal disease surveillance, this kind of things. If you are interested in those topics, I published a book several months ago, just came out maybe half a year ago. You can read this book. This is my last slide. Let me see how much time, yeah. I'm quite lazy. I only listed a very small number of points here. Actually, all those research topics are quite new, and there are many large number of open research problems. Remember, for dynamic process monitoring, I always assume the period is 1 year. For example, infectious disease, why exactly 1 year? This year, the period could be 11 months. Next year, maybe a little bit longer, the period. So you see, so how to choose the initial in-control data? How about we don't have sufficient in-control data? How to estimate the period? And after we got the signal, how to tell people where, when the detected shift started and where the detected shift started, where are the anomalous regions, so on and so forth. There are a large number of research questions actually in those areas. So let me just stop here to see whether you have any questions.
Yeah, thank you, Professor Qiu. So I think it's very comprehensive and very insightful talk. Thank you so much. Yeah, let's see whether we have some questions from the audience.
Audience, please feel free to unmute yourself if you have any questions. And you can also type questions in the chat box.
Yeah, let me just serve as a icebreaker. Yeah, I personally very enjoy the work on the TSA. So essentially, the idea is say, okay, we have some in-control data, then do the phase 1 analysis. We can build some control limit. Then we have the online monitoring, then we can do the updating. So, but maybe you show somewhere in the slides, but I'm just not careful that much. Can you show me the monitoring statistic you construct?
Okay, let me see. Monitoring statistics.
I suppose you're going to use the estimated mu, sigma, and the correlation, but I didn't see like which specific way you combine them together to contribute to threshold or monitoring statistic.
I didn't provide. I'm so sorry.
Okay.
I said here we need to apply a multivariate non-parametric Q-sum chart to the standardized data. And I can tell you how, because all those, this is a Technometrics paper, all those methodologies are developed by myself.
Okay.
So suppose this is the standardized data and already do the decorrelated and standardized data. It's a vector. And then we decorrelate data because it's non-parametric. We don't know its distribution. So we, for each component, we decorrelate data. How to decorrelate data? For example, we decorrelate categorize data. I'm so sorry. Categorize data. For example, each component, we categorize data into two categories, compare with the mean, integer mean. It's above integer mean or below integer mean. So then each component now becomes categorical data. Then you have multivariate categorical data. Then we use log linear modeling. Log linear modeling is a statistical approach to describe multivariate categorical data. Based on that, we construct a control chart. We construct Q-sum chart. Basically, you compare the observed count and expected count. Because categorical data, now we have contingent table, we have counts, observed count and expect count. So we have Pearson's chi-square statistic. By using the Pearson's chi-square statistic, we make it a Q-sum version, cumulative sum version. And then that's the control chart. It's quite complicated. That's why I didn't present it here.
Yeah, so it seems like it really depends on the decorrelation, right? Because to apply your method like here in the 2003 Technometrics paper, it should be a decorrelated data, right? So that you can.
Yeah, decorrelated data, and the data decorrelation depend on the estimated covariance.
Yeah, so this is actually my question. So the estimated covariance, will that be updated during?
Updated, yes. Everything is updated.
Okay. So in that case, let's think about a case like if you keep feeding those out of control data, right? Then you are still updating, but in that case, your updated covariance gradually represent the out of control data. Then you still rely on that to do the, yeah.
This is a very good question. Very good question. That's the limitation of self-starting control chart. Self-starting means the in-control parameter estimate need to be keep updated. But how about you didn't detect the shift on properly, so that some out-of-control data will be used in updating.
Yes.
We already noticed that, and in one of our paper we said we will only use the observed data collected before the restarting mechanism. Remember, Q-sum has a restarting mechanism. So we only use the historical data collected before the previous restarting mechanism, restarting time.
Oh, okay.
To avoid that.
Okay. Yeah, but this might be too detailed. But that also depends how you decide the restarting, right? So that also has some.
No, restarting mechanism. Q-sum has a restarting mechanism. Remember, Q-sum is a maximum 0 or something like that.
Yeah.
If the charting statistic is below minus k, if the cumulative sum smaller than or equal to k, then the charting will reset to 0.
Yes.
That's called the restarting mechanism.
Yeah.
So because after restarting mechanism, the chance to have out of control data will be very high. But before the restarting mechanism, we are quite certain the process is in control. So we only use the data before the previous restarting time.
Okay. So that essentially means those are more likely to be in control data.
Yes, exactly. Yeah.
Okay. Yeah, thank you. That's an insightful strategy. Yeah, thanks. Yeah, I think we have a question in the chat box say, can we use SPC or control charts to monitor readmission of patients as a time to event variable?
Yes, we can. We can. Definitely. The number of the registered patients, actually a couple of years ago, the Philadelphia Children's Hospital invited me to give a talk because those hospitals, they have a lot of such data, number of registered patients and patient visits. Each day they have a patient visits. They want to monitor those. And I tell them how to monitor those. Yes, we can.
Thank you, Professor Cho, again for your wonderful presentation and all the research achievement, especially in um, transparent sequential learning, dynamic screen, and also, as well as spatial temporal modeling. So Mike, I have one question about spatial temporal modeling. Um, Compared to the vector-based modeling, right? Is there any unique challenge exists in the spatial temporal modeling? Because spatial temporal data are quite different.
Yeah. Spatial temporal modeling is a very complicated problem, actually. I started to do research in this area after I came to UF about 12 years ago to develop the brand new biostat department. Why I started doing research in this area? Because we have an infectious disease research center. And then after I talked to our faculty members, I try to understand what they are doing. And then a lot of data are spatial temporal data. And the approach they use, I thought that will never work because they assume data IID, normal, this kind of, I said, no. So then that's about the time I started doing my own research in this area. Why it's complicated? Because there is a spatial temporal correlation.
Mm-hmm.
Most people try to ignore such a spatial temporal correlation. Intuitively, if the two observations, they are very close in time or space or location, they are more correlated. That's because, for example, those spatial temporal correlations are reflection of the so-called confounding risk factors. Because the people in those places are more similar, and so those are the reflects the impact of the confounding risk factors like cultures, living, people's behaviors, and those confounding risk factors. So if we double check those spatial temporal correlations, almost every data have a very strong spatial temporal correlations, and those spatial temporal correlations are so difficult to describe statistically. How to describe them? And people try in statistics, we have a research area called spatial statistics. Spatial is a big research area in statistics. But those the majority of those existing methodologies, they try to use parametric spatial modeling, Bayesian modeling, this modeling, that modeling. Why? Because in those in their applications, the data points are quite sparse. They don't have many data points. So they tend to develop some parametric spatial models. But in this business, in disease surveillance, those business, we have so many data points. We have data over different locations and every day, even sometimes every hour. So we have a lot of data. So that's why I said, well, we should develop more flexible models. So all of my models are non-parametric. And the complexity because the spatial temporal correlations are so difficult to describe and to estimate. That's the complexity. Yeah.
Mm-hmm.
And they cannot be ignored, by the way. I read many I have so many friends in industrial engineering community, and you guys usually develop a very complicated methodology, but don't check the assumptions carefully. So if you don't check those assumptions, I already show you some plots. That's the consequence. Those methods will not be reliable.
Mm-hmm. Yeah, we're missing data will also be some issue. For example, at some special locations, at this moment we have data, but next day we don't have data at all.
You are right. But in this business, my methodology is I use local smoothing. It's more flexible. if you have the next day, some places does not have, in my modelings, the number of location could be different at different time points. So this kind of flexibility, and also I use Kuno smoothings, Kuno smoothing weighted averages. I weighted average of all available data. If the data are not available, they didn't. So that's the issue, but it's not a serious issue in this specific problem because we have a lot of problems. Otherwise, how to impute missing value is a research problem otherwise.
Yeah, thank you so much for the insightful explanation.
Yeah.
Yeah, let's see whether we have any question from audience. Yeah, maybe I can ask the final question to end this wonderful talk. So yeah, regarding your third work, actually you have a pre-processing procedure for the PCA, right? So in the PCA, actually the how to say high level idea is to do a data projection. And we project to the largest variance, hyperdirection, right?
Yeah.
So in this case, why? Of course, this is a very regularly used method to do data dimensional reduction. But why do we project the data to the largest variance axis or those direction can be helpful for doing change detection, right? Because think about if we have an ellipse, right? We have an ellipse. That ellipse, you can do the PCA, you project to the long axis, right? But we know the outlier can also happen at the short axis, right? So if you do that projection, you kind of collapse and contaminate that outlier information. Do you have any insights? I see a lot of work, change detection, change point detection. They use PCA to do dimension reduction.
First of all, PCA is unsupervised dimension reduction techniques. Means you only have X, you don't have Y. If you have Y, then I will not use PCA. But here we don't have Y. Y, for example, we know each observation is in control or out of control. If we have that information, I will not use PCA. Here, because we don't have Y, so I use PCA. That's one. Two, Chao, I would suggest you take a course called multivariate statistics. I myself taught that course 6 or 7 times when I was a professor in Minnesota. In that course, when I teach students about PCA, why we need to project in statistics, variability of a variable denote the amount of information in the observed data. So why we project to the direction that the variability in that direction is the largest. That's the first PCA. Because that direction, variability is the largest. That means that direction, we keep the largest amount of information. Just to give you an extreme example, suppose we have a group of people, all those people, their age is 22 years old. All the students, their age is 22. So the variability is 0. Now, in such a group, for such data, do you think age, that variable will carry any, besides we know all those people are 22 years old. Other than that, that variable didn't provide us any other information about that group of people. So in statistics, the variability of a variable describes the amount of information contained or carried by this variable. That's why we project the first PCA is we project the data into the direction that the variability is the largest.
Yeah. I think I understand the PCA, but my question is, if we apply the decomposed component into the change detection, will that also be affected by the out of control pattern, right? Because just like the example I just take, like if we have an ellipse, we have the long one and the short one. The out of control data can also happen at the short direction, right? The short axis direction. If we do the PCA, we kind of squeeze into the long direction one. Then
you see there's a big difference. Then that big difference will be detected. The out of control and in control are so different, then that will be detected. So you see,
Okay.
PCA want to reduce the dimensionality, but we want to, on one side, we want to reduce the dimensionality. On the other side, we don't want to give up, lose a lot of information. That's the basic idea of PCA. Yeah.
I see. Okay. Yeah, thank you. Thank you so much. Yeah. And yeah, I think we just exactly use the time, so which is great.
Yeah, okay. Thank you so much for coming, and I appreciate your attendance.
Yeah, thank you, all the attendants. And this video is recorded, and we will post on the YouTube and Informs QSR LinkedIn page within 2 weeks after today's webinar. Yeah, and thank you everyone for attendance, and especially thank you, Dr. Qiu, yeah, for this wonderful talk.
Thank you. Take care, and see you in the Informs or other occasions. Take care.
Sure, sure.